Hello everyone, this is Reshma from Edureka, and today we are all learning Hadoop and Spark. Even if you all are new to these technologies, and since this is the first class, but I will assure you that at the end of this session, you'll be very confident about Hadoop and Spark and start feeling like an analyst already. So this session is going to be a little different because we thought that the best way of learning something is by implementing it. So we will learn Hadoop and Spark by implementing real-life use cases directly, and I'm sure that you will all have a great time going through that. So these are the two use cases that we'll be dealing with today. The first is the US primary election analysis, and the second is the instant cabs use case. So we will begin with the US primary election analysis first, and we'll be talking about the primary election in 2016. So you know that in the primary elections from Democrat, the two contenders were Hillary Clinton and Bernie Sanders, out of which Hillary Clinton won the primary elections from Democrats, and Republicans there was Donald Trump, Ted Cruz, and a few other contenders, out of which Donald Trump won the primary elections. So now, let us assume that you are an analyst already, and you have been hired by Donald Trump, and he tells you that I want to know that what were the different reasons because of which Hillary Clinton won. And I want to carry out my coming campaigns based on that so that I can win the favor of the people that voted for her, so that I can take away her votes and finally become the president. So that was the entire agenda. So this is the task that has been given to you as a data analyst. So what is the first thing that you will do? The first thing you'll do is that you'll ask for data. And you have got two data sets with you. The first is the US primary election data set, and the second is the US demographic features county-wise data set. So let us take a look at what these data sets contain. So this is our first data set, which is the US primary election data set. So these are the different fields present in our data set. So the first field is state. So we have got the list of the state Alabama, the state abbreviation. So for Alabama, it's AL. We've got the different counties in Alabama like Ottawa, Baldwin, Barber, Bibb, Blount, Bullock, Butler, etc. And then we have got FIPS. Now FIPS are Federal Information Processing Standards Code. So this basically means zip code. Then we've got the party. So we will be analyzing the Democrats only because we want to know what was the reason for Hillary Clinton's win. So we'll be analyzing the Democrats only. And then we've got the candidate. And since I told you that there were two candidates, Bernie Sanders and Hillary Clinton, so we've got the name of the candidate here and the number of votes that each candidate got. So Bernie Sanders got 544 in Ottawa County and Hillary Clinton got 2,387. And this field over here represents the fraction votes. So if you add this two together, you'll get a 1. So this basically represents the percentage of vote each of the candidates got. So let us take a look at our second data set now. So this is the US County Demographic Features dataset. So first field we have again the FIPS, the area name, the Ottawa County, Baldwin, and different other counties in Alabama and other states also. The state abbreviation, so here it is only showing Alabama. And the fields that you see here are actually the different features. You won't know what this exactly contains because it's written in a coded form. But let me give you a few examples what this dataset contains. Let me tell you that I'm just showing you a few rows of the dataset. This is not the entire dataset. So this contains different fields like population in 2014, in 2010, the sex ratio, how many females, males, then based on some ethnicity, how many Asians, how many Hispanic, how many Black American people, how many Black African people. Then there is also based on age groups, how many infants, how many senior citizens, how many adults. So there are a lot of fields in our data set. And this will help us to analyze and actually find out what led to the winning of Hillary Clinton. So now you have seen your data set. You have to understand your data set. You have to figure out what were the different features or what are the different columns that you're going to use. And then you have to think of a strategy or think of how you're going to carry out this analysis. So this is the entire solution strategy. So the first thing you'll do is that you need a data set, and you have got two data sets with you. The second thing you need to do is that you need to store that data into HDFS. Now HDFS is Hadoop Distributed File System, so you need to store that data. The next step is to process that data using Spark components, and we'll be using Spark SQL, Spark MLlib, etc. The next task is to transform the data using Spark SQL. Transforming here means filtering out the data and the rows and columns that you might not need in order to implement or in order to process this. The next step is clustering this data using Spark MLlib. And for clustering our data, we'll be using k-means. And the final step is to visualize the result using Zeppelin. Now, visualizing this data is also very important because without the visualization, you won't be able to identify what were the major reasons and you won't be able to gain proper insights from your data. Now, don't be scared if you're not familiar with terms like Spark SQL, Spark MLlib, k-means clustering. You'll be learning all of this in today's session. And so this is the entire strategy. This is what we're going to do today. This is how we're going to implement this use case and find out why Hillary Clinton won. So now let me just give you a visualization of the results. So I'll just show you the analysis that I have performed and I'll just show you how it looks like. So this is Zeppelin, which is in my master node in my Hadoop cluster. And this is where we're going to visualize our data. So there is a lot of code. Don't be scared. This is just Scala code with Spark SQL. And at the end, you'll be learning how to write this code. So I'm just jumping on to the visualization part. So this is the first visualization that we have got, and we have analyzed it according to different ethnicities of people. For example, in our x-axis, we have got foreign-born persons, and in y-axis, we're seeing that among the foreign-born people, what is the popularity of Hillary Clinton among the Asians? And the circles represent the highest values. The bigger the circle is, the bigger the count. So we have made a few more visualizations. So now we have got a line graph that compares the votes of Hillary Clinton and Bernie Sanders together. Again, we have got an area graph also that compares Bernie Sanders and Hillary Clinton votes. And hence we have got a lot more visualizations. We've got bar charts and everything. And finally, we also have a state and county-wise distribution of votes. So these are the visualizations that will help you to derive a conclusion, to derive an answer, whatever answer that Donald Trump wants from you. And don't worry, you'll be learning how to do that. I'll explain each and every detail of how I have made these visualizations. So now let us take a look at our second use case, which is the instant cabs use case. So now there is a cab startup in US, which is called Instant Cabs. And again, since you did a very great job in analyzing the US elections, so they have hired you again to solve their problem now. So basically, this company wants to know what is the demand of cabs at which pinpoint location during which peak hours. And what they want to do is they want to maximize their profit by finding out the beehive points where they can get a lot of pickups and getting cabs there during the peak hours. So this is your second task. So again, the first thing is that you need a data set. So this is the Uber dataset that has been given to you in order to analyze and find out what were the peak hours and how much cabs are expected in those locations during the peak hours. So this is just a date time stamp. So this represents a pickup time and pickup date for a particular Uber ride. So this is January 2014 and it's around midnight. And then you have got latitude and longitude. So this represents the location of the pickup. And then this is base, which is a TLC base code. So this is like the license number of the driver. So now again, we have to make a strategy of how you are going to analyze this data. So at first you have got your data set in CSV format. So this is your first step. You have got the data. Then the next step again is to store the data in HDFS like we did the first time. Then again, we have to transform the data because this data set actually is really long. It contains a lot of rows and columns, and maybe you don't want to analyze all of them at once. So you will again filter out some of the rows. And after it's transformed, you'll start clustering again with k-means. Again, I'm going to tell you that don't worry, I'm going to explain you k-means from the start and how to do it. And by cluster, we'll find out the center points of each cluster, which will represent each of the pickup point or each of the beehive point. So that's why we're performing clusters in order to find out the cluster centers, which will represent a beehive point where we'll be expecting maximum number of pickups during peak hours. So this is your entire strategy. Now let me just show you the visualization of this one also, like I did it for the US elections. So here is our code again, which is a Scala and a Spark SQL code. So let me just jump directly to the visualization part. So this is again, we have in our x-axis, we have the count or the number of pickups. In the y-axis, we have hours, that is the time of the day. And then we have grouped it according to the size of the count, that is number of pickups. So you can see the largest size that you can see here are these ones, and this is found in the fourth cluster, and it's found at the 17th hour, which is around 5 p.m. So this is what we found out after we have analyzed and visualized our dataset, our Uber dataset. So again, I'll be talking about how many clusters are to be made and how to make different clusters and how to find everything out. So this is again the visualization of the Uber dataset. And then this one represents the location in order to identify the beehive points. So again, we have classified the number of pickups according to the different hours of the day. So we have got 24 slices over here. So you can see the biggest slice, you can see it in the 17th hour and the 16th hours, which is around 4 or 5 p.m. So this is the visualization of the dataset. So let us go back to our presentation. Now we have seen that what we have to do, but now let us understand what it takes in order to perform all this. What are the things that you need to be aware of or you need to learn? So here is what you need to learn in order to perform the analysis on the two use cases. So we'll start with the introduction to Hadoop and Spark. So we'll understand what is Hadoop and what is Spark. And then we'll take a deep dive into Hadoop to understand the different components of Hadoop. For example, the storage unit of Hadoop, which is known as HDFS, and then Yarn, which is the processing unit of Hadoop. And then we'll be using different tools like Apache Spark, which could be easily integrated with Hadoop in order to perform a better analysis. And then we'll understand k-means and Zeppelin because we have used k-means clustering in order to cluster our data, and we have used Zeppelin in order to visualize it. And then we'll finally move on to the solution of use cases where we'll be implementing it directly. So this is what you need to learn. So let us get started with Hadoop and Spark. So we'll start with Introduction to Hadoop and Spark. So now let us take a look at what is Hadoop and what is Spark. So Hadoop is a framework where you can store large clusters of data in a distributed manner and then process them parallelly. Then Hadoop has got two components. For storage, it has HDFS, which stands for Hadoop Distributed File System. So it allows to dump any kind of data across the Hadoop cluster and it'll be stored in distributed manner in commodity hardware. And for processing, you have got Yarn, which stands for Yet Another Resource Negotiator. And this is the processing unit of Hadoop, which allows parallel processing of the distributed data across your Hadoop cluster in HDFS. Then we have got Spark. So Apache Spark is one of the most popular projects by Apache, and this is an open source cluster computing framework for real-time processing, where on the other hand, Hadoop is used for batch processing, Spark is used for real-time processing. Because with Spark, the processing happens in memory, and it provides you with an interface for programming entire clusters with implicit data parallelism and fault tolerance. So what is data parallelism? Data parallelism is a form of parallelization across multiple processors in parallel computing environments. A lot of parallel words in that sentence. So let me tell you simply that it basically means distributing your data across different nodes which operate on the data parallelly. And it works on fault-tolerant systems like HDFS and S3. And it is built on top of Yarn because with Yarn you can combine different tools like Apache Spark for better processing of your data. And if you see the topology of Hadoop and Spark, both of them have the same topology, which is a master-slave topology. So in Hadoop, if you're considering in terms of HDFS, the master node is known as name node, and the worker node or the slave nodes are known as data node. And in Spark, the master is known as master, and the slaves are known as worker. So these are basically daemons. So this is a very brief introduction to Hadoop and Spark. So now let us take a look at Spark complementing Hadoop. So there always has been a debate about what to choose, Hadoop or Spark, but let me tell you that there is a stubborn misconception that Apache Spark is an alternative to Hadoop and that it is likely to bring an end to the era of Hadoop. It is very difficult to say Hadoop versus Spark because the two frameworks are not mutually exclusive, but they are better when they are paired with each other. So let us see the different challenges that were addressed when we are using Spark and Hadoop together. Now you can see the first point that Spark processes data 100 times faster than MapReduce. So it gives us the results faster and it performs faster analytics. The next point is that Spark applications can run on Yarn leveraging Hadoop cluster. And you know that Hadoop cluster is usually set up on commodity hardware, so we are getting better processing, but we're using very low cost hardware. So this will help us to cut our cost a lot. So hence, you also achieve cost optimization. Third point is that Apache Spark can use HDFS as storage. So you don't need a different storage space for Apache Spark. It can operate on HDFS itself, so you don't have to copy the same file again if you want to process it with Spark. So hence you avoid duplication of files. So Hadoop forms a very strong foundation for any of the future big data initiatives, and Apache Spark is one of those big data initiatives. It has got enhanced features like in-memory processing, machine learning capabilities, and you can use it with Hadoop, and Hadoop uses commodity hardware which can give you the better processing with minimum cost. So these are the benefits that you get when you combine Spark and Hadoop together in order to analyze big data. So now let us see some of the big data use cases. So the first big data use case is web and e-tailing. So the recommendation engines, whenever you go out in Amazon or any other online shopping site in order to buy something, you'll see some recommended items popping below your screen or at the side of your screen. So that is all generated using big data analytics. Ad targeting, you go to Facebook, you see ads of different items asking you to buy them. Then you've got search quality, abuse and click fraud detection. You can use big data analytics in telecommunications also in order to find out the customer churn prevention, the network performance optimization, analyzing network to predict failure, and you can prevent loss before the error or before the fault actually occurs. It is also widely used by government for fraud detection and cybersecurity in order to introduce different welfare schemes, justice. It has been widely used by healthcare and life sciences for health information exchange, gene sequencing, serialization, healthcare service quality improvements, drug safety. And let me tell you that with big data analytics, it has been very easy in order to diagnose a particular disease and find out the cure also. So these are some more big data use cases. It is also used in banks and financial services for modeling true risk, fraud detection, credit card scoring and analysis, and many more. It can be used in retail, transportation services, hotels and food delivery services. Actually, every field you name, no matter whatever business you have, if you are able to use big data efficiently, your company will grow and you'll be gaining different insights by using big data analytics and hence improve your business even more. Nowadays, everyone is using big data. You have seen the different fields. Everything is different from each other, but everyone is using big data analytics. And big data analytics can be done with tools like Hadoop, Spark, etc. So that is why big data analytics is very much in demand today, and that is why it is very important for you to learn how to perform big data analytics with tools like this. So now let us take a look at a big data use case solution architecture as a whole. So you're dealing with big data now. So the first thing that you need to do is you need to dump all those data into HDFS and store it in a distributed way. The next thing is to process that data so that you can gain insights, and we'll be using Yarn because Yarn can allow us to integrate different tools together which will help us to process the big data. So these are the tools that you can integrate with Yarn. So you can choose either Apache Hive, Apache Spark, MapReduce, Apache Kafka in order to analyze big data. And Apache Spark is one of the most popular and the most widely used tool with Yarn in order to process big data. So this is an entire solution as a whole. So now since we have got introduced to Hadoop and Spark, let us take a deep look at HDFS, which is the storage unit of Hadoop. So HDFS stands for Hadoop Distributed File System, and this is the storage unit for Hadoop. And here is the architecture of HDFS. So in HDFS you've got, and since I already told you that it is a master-slave architecture, so the master node is known as name node and the slave nodes are known as data nodes. And then we have got another node here which is known as secondary name node. Now don't get confused that secondary name node is just going to be a replacement for name node, because it is not. So I'll tell you what a secondary name node does. So now let's go back and understand the entire architecture properly. So you can see the little icons over all of these different nodes. So basically, name node is the master daemon, so you can think of it as the king. It has got a helper daemon, which is a secondary name node, which has the icon of the minister. And then the pawns represent the slave nodes or the slave daemons. Data node over here, it contains the actual data. So whenever you dump a file into HDFS and it gets distributed, your data is stored in the data nodes. And the best thing about HDFS is that it creates an abstraction layer over the distributed storage resources. So when you're dumping the file in HDFS, it gets distributed in different machines. But you can see the entire HDFS as a single unit because it is laid out in such a structure. So now let us view each of these components one by one. So first, we'll take a look at the name node. So the name node is the master daemon and it maintains and manages the data node. So what a name node does is that it preserves a metadata. A metadata meaning data about data. So whatever file or whatever data is stored in the data nodes, the name node maintains a proper sheet, a proper file where everything is mentioned, that what data is stored in which data node, and it serves any kind of request from the clients also. And since it acts as a master node, it also receives heartbeats, the little hearts you saw popping in the earlier slide. The data nodes are actually sending heartbeats to the name node, which is nothing but signals just to tell the name node that the data node is alive and functioning properly. Now comes the secondary name node. The secondary name node does a very important task, and that task is known as checkpointing. So checkpointing is a process of combining edit logs with FS image. So now let me tell you what is an edit log and what is an FS image. So let's say that I have set up my Hadoop cluster 20 days back, and whatever transactions that happen, whatever new data blocks are stored into my HDFS, whatever data blocks are deleted, every transaction is contained in a file known as FS image. An FS image resides in your disk. And there is one more similar file which is known as edit logs. Now edit logs won't keep the record of transactions 20 days back, but just a few hours back. So let's say it will keep the record and the transaction details that happened in the past 4 hours. And checkpointing is the task of combining the edit log with the FS image. And it allows faster failover as we have a backup of the metadata. So a situation where a name node goes down and the entire metadata is lost, we don't have to worry. We can set up a new name node and get the same transactional files and the metadata from the secondary name node because it has been keeping an updated copy. And checkpointing happens after every 1 hour, but you can also configure it. So let us understand the process of checkpointing in detail. So here is the FS image and the edit log. So the FS image in the disk and the edit log resides in your RAM. So what the secondary name node does is that it first copies the FS image and the edit log and adds them together in order to get the updated FS image. And then this FS image is copied back to the name node, and now the name node has an updated FS image. And in the meantime, a new edit log is created when the checkpointing is happening. So this process keeps going on, and hence it helps the name node in order to keep an updated copy of the FS image of the transactions every hour. So now let us talk about the data nodes. So these are the slave daemons, and this is where your actual data is stored. And whenever a client gives a read or write request, the data node serves it because the data is actually stored in the data nodes. So this is all about the components in HDFS. Now let us understand the entire HDFS architecture in detail. So we have got different data nodes here, and we can set up different data nodes in racks. So in rack 1 we have got 3 different data nodes, and in rack 2 we have got 2 different data nodes. And each of the data node contains different data blocks, because in data nodes the data is stored in blocks. So we'll learn about that in the coming slides. So the client can request for either a read or write. So let's say that the client requests to read a particular file. So it will first go to the name node. Since the name node contains the metadata, the name node knows exactly where the file is. So it will give the IP addresses of the data nodes where the different data blocks are of that particular file. And it will tell the client that you can go to this IP address, you can go to this data node, and you can read the file. And then the client goes to the different data nodes where the data block is present. And finally, the read request is served. And now let's say the client wants to write a file. Again, it will contact the name node, and the name node will check the metadata and will see where space is available and it will check whether space is available or not. And then again, it will give the IP addresses of the data nodes where client could write the file. And similarly, the writing mechanism also happens. So this is how entire read-write request is served by the data nodes and the name node. So now let us talk about HDFS block and replication. And since I've been telling you that HDFS is a fault-tolerant system, let us see how. So each file is stored in HDFS as a block. So whenever you dump a file into HDFS, it breaks down into different blocks and it is distributed across your Hadoop cluster. And the default size of each block is 128 MB. So let's say that I have a file of 380 MB. So it'll be divided up into 3 blocks. So the first block will be of size 128 MB, the second will be 128 MB, and the third will occupy whatever the remaining size of the file is, which is 124 MB. So now tell me that if you have a file size of 500 MB, how many blocks it will create? Alright, so Ajay says 4, Rohit says 4. Of course, guys, you are right. We will have 4 blocks. So the first 3 blocks will be of the size 128 MB, and this last block will just occupy the remaining file size, which is 116 MB. So now let us know what is block replication. So whenever you dump your file into HDFS, first it is divided up into blocks, and then each of the block is copied 2 times. So now you have the original block and 2 more copies of the same block. So replication factor equal to 3 means that there are 3 similar blocks in your Hadoop cluster. So you can see that I have a file of 248 MB, 128 MB, and 120 MB. So my block 1 is there 3 times, and block 2 is also there in 3 times in 3 different data nodes. So we use this replication factor so that if any of the data node goes down, so we can retrieve the data block back from the 2 different data nodes. So this is how data blocks are replicated in HDFS. So now in order to do the replication properly, there is an algorithm which is known as rack awareness, and it provides us optimized fault tolerance. So rack awareness algorithm says that the first replica of a block will be stored in a local rack, and the next 2 replicas will be there in a different rack. So we store a data block in one rack so that our latency is decreased. So now these are the commands that you'll use to start your Hadoop daemons. Your Hadoop daemons like your name node, your secondary name node, and your data nodes in the slave machine. So in order to start all the Hadoop daemons, HDFS and Yarn, so I have not explained you Yarn yet, but Yarn is the processing unit of Hadoop. So it will also start all the Yarn daemons like the resource manager and the node manager also. Then this is the command to stop all the Hadoop daemons, and with JPS you can check what are the daemons that are currently running in your machine. So let me just show it to you. So the first thing that I need to do is I need to change the directory to my Hadoop directory. So I'll just do cd Hadoop, and now I can run all the commands. And you remember the first command was /sbin start_all.sh. So it'll ask for password. Alright, so let me also tell you that you can also configure it to be a passwordless process so that you don't have to enter passwords when it wants to run certain daemons. So let us now use JPS. So here are the daemons that are running in my master. So I've got my node manager, my secondary name node, JPS itself is a daemon, then data node, resource manager, and name node. So I'll tell you all about resource manager and node manager in the coming slides, so don't worry about that. So these are just the daemons that are running in my master machine. Now let me show you what are the daemons that are running in my slave machine. So this is the terminal of my slave machine. So I'm just going to run JPS here, and these are the processes or the daemons that are running in my slave machine. So node manager and data node both are slave daemons, and they are running in my slave machine. So if you want to stop all these daemons, so you can run the same command, only instead of start you can just put a stop here. So since I'm going to use my HDFS, so I'm not going to stop it and show it to you, but the process is same. So these are a few commands that you can use to write or delete a file in Hadoop. So if you want to copy a file from your local file system to your HDFS, you can use this command hadoop fs-put, and this is the name of your file. So you have to type the proper path of the file so that it can copy to HDFS. So you can also mention the destination folder in HDFS where you want to copy it. If you're leaving it blank, it means that it will just copy onto the master directory in Hadoop. Then if you want to list out all the HDFS files, You can do that using this command, and if you want to remove that file, remove the same file, again you can use this command, Hadoop fs-rm, which is used for removing. Now this is also the first step that you need to do when you are starting to analyze something. So this is the same way that we'll copy our data sets into our HDFS first and then analyze it. So we have seen HDFS, now let us take a look at Yarn, which is the processing unit of Hadoop. So what is Yarn? Yarn is nothing but it is MapReduce version 2. So when Hadoop came up with its new version, Hadoop 2.0, it introduced Yarn as the new framework, and it stands for Yet Another Resource Negotiator, and it provides the ability to run non-MapReduce applications. And because of Yarn, we are able to integrate different tools like Apache Spark, Hive, Pig, etc. And it provides us with a paradigm for parallel processing over Hadoop. So when you're dumping all your data into HDFS, it is getting distributed, and all this distributed data are processed parallelly, and it is done with the help of Yarn. So you can see over here the architecture of Yarn. So it is again a master-slave topology. So the master daemon here is known as Resource Manager, and the slave daemons are known as Node Manager. So let us take a look at these components one by one. So first up is the Resource Manager. So this is the master daemon, and it receives the processing request. Whenever a client comes up with a request, he comes to the Resource Manager first, because the Resource Manager manages all the slave nodes or the node managers. So whenever a client comes and he wants to process some data, the Resource Manager takes that request and passes the request to the corresponding node managers. Now let us see what is a node manager. Now node managers are the slave daemons, and they are installed on every data node. So you know that our data is divided up into blocks and are stored in data nodes, and they are processed in the same machine. So in the same machine where the data node is set, a node manager is also present to process all the data present in that data node. And it is responsible for execution of tasks on every single data node. So this is where the actual processing of data takes place. Now let us see the entire architecture in detail. So the client comes up with a request to the Resource Manager in order to process the data. And then the Resource Manager passes on the request to the node managers. So there are these important components that I'm going to talk about, and you should pay attention to it. So in the node manager, we have got a container and an app master. Now an app master is launched for every specific application code or every job or every processing task that the client comes up with. So the application master or the app master is responsible to handle and take care of all the resources that is required in order to execute that code. So if there is any requirement for any resources, it's the app master who asks for the resources from the resource manager, and then the resource manager provides the app master with all the resources, and then it asks the node manager to start a container, and the container is the place where the actual execution happens. So now let us see the entire Yarn workflow in order to understand things better. So here is the client, and this client wants to run a job. So in this example, I'm considering a MapReduce job. So the MapReduce code is first displayed as a MapReduce job, and then the client wants to run this particular job. He submits the job to the resource manager and asks the resource manager to execute this. The resource manager gets back to the client with an application ID for his job. Then the resource manager starts a container where the app master is launched. Now the app master is also launched in a particular container. The app master then gathers all the resource requirements in order to run that job and asks the resource manager to allocate all the resources. After that, when all the resources are provided, the node manager launches a container and starts a container, and this is where the job executes. Now let us take a look at the entire Yarn application workflow step by step. So the first step is the client submits an application to the resource manager. Then the resource manager allocates a container to start the app master. And then the app master registers with the resource manager and tells the resource manager that an app master has been created and it is ready to oversee the execution of the code. Then the app master asks containers from the resource manager. The app master also notifies the node manager to launch containers. And after the containers are launched, the application code is executed in the container, which was the application code of the particular client. And then the client contacts the resource manager to ask for the application status, whether it is executed properly or not. And after it has been executed successfully, the app master unregisters with the resource manager. So this is the entire workflow. Now let us take a look at the entire Hadoop cluster architecture, HDFS with Yarn. So here you can see that both HDFS and Yarn follows a master-slave topology, and the master in HDFS is name node and the master in Yarn is resource manager. The slave daemons in HDFS are the data nodes. This is where all your data is stored. And in Yarn, it is node manager. This is where your data is processed in a container, and the app master takes care of all the resources that is necessary in order to execute your program. So there is one important thing that you should know, and you must have noticed it, that my data node and my node manager will lie in the same machine. So this data node and this node manager will be in the same machine, and this data node and this node manager will be in the same machine. But it is not necessary that the name node and the resource manager would be in the same machine. They could be, but it's not necessary. Now a name node could be in a different machine and a resource manager could be in another machine. Alright? So don't get confused that these two will also be on the same machine, which is not the case. So now let me tell you about the Hadoop cluster hardware specification. Some of the hardware specifics that you should keep in mind if you want to set up a Hadoop cluster. So for the name node, you need RAM with 64 GBs, your hard disk should be minimum of 1 terabytes, the processor should be Xenon with 8 cores, the Ethernet should be 3 by 10 GB per second, the operating system should be 64-bit CentOS or Linux, the power should be redundant power supply because you don't want the name node to go down, right? Because if the name node goes down, your entire HDFS cluster will go down. And for the data node, you need 16 GBs of RAM. Hard disk should be 6 into 2 terabytes because this is where you'll be storing all your data, so it needs to have a lot of memory. The processor should be Xenon with 2 cores, Ethernet 3 by 10 Gbps, and 3 by 10 GB per second, and OS should be again 64-bit CentOS or Linux. And for the secondary name node, your RAM should be 32 GBs, your hard disk should be 1 terabyte, processor Xenon with 4 cores, Ethernet 3 by 10 GB per second, OS should be 64-bit CentOS Linux, and power again should be a redundant power supply. Now you might pause your screen and take a look or take a screenshot of this image, and don't worry, this presentation and this recording would be there in your LMS as well. So this is what you should keep in your mind. So if you're setting up a Hadoop cluster, so these are the hardware specifications required to do that. Now let me tell you about some real-time Hadoop cluster deployment. So let us consider our favorite example, which is Facebook. So Facebook has got 21 petabytes of storage in a single HDFS cluster. And 21 petabytes is equal to 10 raised to the power of 15 bytes. And they have got 2,000 machines per cluster and 32 GBs of RAM per machine. They run 15 MapReduce tasks, and each of these machines run 15 MapReduce tasks. And 1,200 machines have 8 cores each, and 800 machines have 16 cores each. And there are 12 terabytes of data per machine. So it has got a total of 21 petabytes of configured storage capacity, and it is larger than the previous known Yahoo's cluster, which was known to be the largest Hadoop cluster. It was a 14 petabytes, so Facebook has beaten Yahoo with 21 petabytes. And now let's talk about another use case, which is Spotify. So how many of you listen music in Spotify? Alright, so it looks like some of you do. So even Spotify uses Hadoop for generating music recommendations, because when you're listening to music, you'll see that some of the music, some new songs are recommended to you, which also belongs to the same genres that you have been listening to, right? So it is done by big data analysis with Hadoop. And Spotify has got 1,650 node clusters, and they have got 65 petabytes of storage approx. And Spotify has 70 TB of RAM, and they run more than 25,000 daily Hadoop jobs, and it has got 43,000 virtualized cores. So it is even a larger cluster than Facebook, right? So these were two use cases who use a Hadoop cluster in order to process and store big data. So now you have learned all about Hadoop, the HDFS and Yarn, both the storage and the processing component of Hadoop. So now let us take a look at Apache Spark. So Apache Spark is an open source cluster computing framework for real-time processing, and it has been the thriving open source community and is the most active Apache project at this moment. And Spark components are what make Apache Spark fast and reliable. And a lot of Spark components were built to resolve the issues that cropped up while using Hadoop MapReduce. So Apache Spark has got the following components. It has got the Spark core engine. Now the core engine is for the entire Spark framework. So every little component is based on and it is placed on the core engine. So at first we've got Spark SQL. So Spark SQL is a Spark module for structured data processing. And it can run unmodified Hive queries on existing Hadoop deployment. And then we've got Spark Streaming. Now Spark Streaming is the component of Spark which is used to process real-time streaming data. And it is a useful addition to the core Spark API because it enables high throughput and fault-tolerant stream processing of the live data streams. And then we have got Spark MLlib. So this is the machine learning library for Spark, and we'll be using Spark MLlib in order to implement machine learning in our use cases too. And then we've got GraphX. This is the graph computation engine, and this is the Spark API for graphs and graph parallel computation. So it has got a set of fundamental operators like subgraph, join vertices, etc. And then you've got Spark R. So this is a package for R language to enable our users to leverage Spark power from R shell. So the people who have already been working on R and they're comfortable with R, so they can use the R shell directly and at the same time can use Spark using this particular component, which is Spark R. So you can write all your code in the R shell and Spark will process it for you. Now let us take a deeper look at all these important components. So we've got Spark Core, and Spark Core is the base engine for large-scale parallel and distributed data processing. The core is the distributed execution engine, and the Java, Scala, and Python APIs offer a platform for distributed ETL application development. And further, additional libraries which are built on top of the core allow diverse workloads for streaming, SQL, and machine learning. It is also responsible for scheduling, distributing, and monitoring jobs in a cluster, and also interacting with storage systems. Now let us take a look at the Spark architecture. So Apache Spark has a well-defined and layered architecture where all the Spark components and layers are loosely coupled and integrated with various extensions and libraries. So first let us talk about the driver program. So this is the Spark driver, which contains the driver program and Spark context. So this is the central point and entry point of the Spark shell. And the driver program runs the main function of the application and is the place where Spark context is created. So what is Spark context? Spark context represents the connection to the entire Spark cluster, and it can be used to create resilient distributed datasets, accumulators, and broadcast variables on that cluster. And you should know that only one Spark context may be active per Java virtual machine. And you must stop any active Spark context before creating a new one. So let's talk about the driver program. So driver program that runs on the master node of the Spark cluster, it schedules the job execution and negotiates with the cluster manager. So this is the cluster manager over here. So the cluster manager is an external service that is responsible for acquiring resources on that Spark cluster and allocating them to a Spark job. And then in the worker node we have got the executors. So the executor is a distributed agent that is responsible for the execution of tasks. And every Spark application has its own executor process. So executors usually run for their entire lifetime of a Spark application, and this phenomenon is also known as static allocation of executors. But you can also opt for dynamic allocations of executors where you can add or remove Spark executors dynamically to match with the overall workload. Okay? So now let me tell you that what actually happens when a Spark job is submitted. So when a client submits a Spark user application code, the driver implicitly converts the code containing transformations and actions into a logical directed acyclic graph or DAG. And at this stage, the driver program also performs certain kinds of optimizations like pipelining transformations and then converts the logical DAG into a physical execution of plan with a set of stages. And after creating the physical execution plan, it creates small physical execution units that are referred to as tasks under each stage. And these tasks are bundled to be sent to the Spark cluster. So the driver program then talks to the cluster manager and negotiates for resources. And the cluster manager then launches the executors on the worker nodes on behalf of the driver. And at this point, the driver sends tasks to the cluster manager based on the data placement. And before the executors begin execution, they first register themselves with the driver program so that the driver has got a holistic view of all the executors. Now the executors will execute the various tasks that is assigned to them by the driver program. And at any point of time when the Spark application is running, the driver program will keep on monitoring the set of executors that is running the Spark application code. And the driver program here also schedules future tasks based on data placement by tracking the location of the cache data. So I hope that you've understood the architecture of Spark. Any doubts? All right, no doubts. Now let us take a look at Spark SQL and its architecture. So Spark SQL is the new module in Spark, and it integrates relational processing with Spark's functional programming API. And it supports querying of data either via SQL or via Hive query language. So for those of you who have been familiar with RDBMS, so Spark SQL will be a very easy transition from your earlier tools because you can extend the boundaries of traditional relational data processing with Spark SQL. And it also provides support for various data sources and makes it possible to weave SQL queries with code transformation, and that is why Spark SQL has become a very powerful tool. So this is the architecture of Spark SQL. So let's talk about each of these components one by one. So first we've got the data source API. So this is a universal API for loading and storing structured data. And it is built on support for Hive, Avro, JSON, JDBC, CSV, Parquet, etc. It also supports third-party integration through Spark packages. Then we've got the data frame API. So a data frame API is the distributed collection of data that is organized into named columns. And it is similar to a relational table in SQL that is used for storing data in tables. Now it is also domain-specific language applicable or DSL applicable on structured and semi-structured data. So it processes data from kilobytes to petabytes on a single node cluster to a multi-node cluster, and it provides different APIs for Python, Java, Scala, and R programming. So I hope that you've understood about the architecture of Spark SQL. So we'll be also using Spark SQL in order to solve our use cases. So these are the different commands to start the Spark daemons. So these are very similar to the Hadoop commands to start the HDFS daemons. So you can see to start all the Spark daemons, so the Spark daemons are master and worker. So you can use this command to check if all the daemons are running on your machine. You can use JPS just like Hadoop. And then in order to start the Spark shell, you can use this. So you can go ahead and try this out. It's very similar to the Hadoop part that I just showed you earlier, so I'm not going to do it again. So we have seen Apache Spark also, so now let us take a look at k-means and Zeppelin. So k-means is the clustering method and Zeppelin is what we're going to use in order to visualize our data. So let's talk about the k-mean clustering now. So k-means is one of the most simplest unsupervised learning algorithms that solve the well-known clustering problem. So the procedure of k-means follows a simple and easy way to classify a dataset through a certain number of clusters, which is fixed prior to performing the clustering method. So the main idea is to define k centroids, one for each cluster, and these centroids should be placed in a very cunning way because of different location causes different results. So here let us take an example. So let's say that we want to cluster total population of a certain location. So we want to cluster them into 4 different clusters, namely group 1, 2, 3, 4. So the main thing that we should keep in mind is that the objects in group 1 should be as similar as possible, but there should be much difference between an object in group 1 and 2. It means that the points that are lying in the same group should have similar characteristics, and it should be different from the points that are lying in a different cluster. And the attributes of the objects are allowed to determine which objects should be grouped together. For example, let us take in the same example that we are using, the US county. So let us consider the second data set that we have used. So there are a lot of features that I already told you. There are age groups, and they are categorized by professions, And they're also categorized by their ethnicity. So this is the thing that we are talking about. So these are the attributes that will allow us to cluster our data. So this is k-means clustering. So here is one more example. So let us consider a comparison on income and balance. So in my x-axis, I have got the gross monthly income, and in the y-axis, I have got the current balance. So I want to cluster my data according to these two attributes. So here if you see, this is my first cluster and this is my second cluster. So this is the cluster that indicates people who have got high income but low balance in their account. They spent a lot. And this cluster comprises of the people who have got low income but high balance. They save. So you can see that all the points that are lying here have got the similar characteristics, that they have got a low income and high balance. And here the people share the same characteristics where they have got low balance but high income. And there are a few outliers here and there, but they don't form a cluster. So this is an example of k-means clustering, so we'll be using that in order to solve our problems. So does anybody have any questions? All right, so here is one more example and one more problem for you, so you guys will tell me now. So the problem is that I want to set up schools in my city, and these are the points which indicate where each of the student lives. So my question to you is, where should I be building my school if I have students living around the city in this particular locations? And in order to find out that, we will do k-means clustering and we'll find out the center points, right? So if we can cluster and make groups of all these locations and set up schools at the center point of each cluster, then that would be optimum, isn't it? Because that is how the students have to travel less. It will be close to everyone's house. And there it is. So we have formed 3 clusters. So you can see the brown dots are one cluster, then the blue dots are one cluster, and the red dots are one cluster. And we have set up schools in the center points of each of the cluster. So here is one, and here is one, and here is got another one. So this is where I need to set up my school so that my students do not have to travel much. So that was all about k-means, and now let us talk about Apache Zeppelin. So this is a web-based notebook which brings in data ingestion, data exploration, visualization, sharing, and collaboration features to Hadoop and Spark. So you can see that, so remember when I showed you my Zeppelin notebook, you can see that we have written the code there, we have even run SQL codes there, and we have made visualizations by executing code there. So this is how interactive Zeppelin is, and it supports many interpreters. And it is a very powerful visualization tool that you can use that goes on very well with Linux systems, and it supports a lot of language interpreters. It supports R, Python, and a lot of other interpreters. So now let us move on to the solution of use case, and this is what you have been waiting for. So at first we'll solve our US County solution. So the first thing we'll do is we'll store the data into HDFS, then we'll analyze the data using Scala, Spark SQL, and Spark MLlib. And then finally, we'll find out the results and visualize them using Zeppelin. So this was the entire US election solution strategy that I told you. I don't think I should repeat it again, but if you want me to, I can. So should I repeat? Alright, so most of the people are saying no, so I'll not go through this one again. So let me just go to my VM and execute this for you. So this is my Zeppelin, and I'll open my notebook here and let us go to my US election notebook. And this is the code. So first of all, what I'm doing is that I'm importing certain packages because I'll be using certain functions that are in those packages. So I have imported Spark SQL packages, and then I have also imported Spark MLlib packages because I'll be using k-means clustering. So vector assembler enables me certain machine learning functions. So over here, the vector assembler package gives me certain machine learning functions that I'm going to use. So I've also imported the k-means package because I'll be using k-means clustering. Then the first thing that you need to do is that you need to start the SQL context. So I have started my Spark SQL context here. And the next thing that you need to do is that you need to define a schema. Because when we want to dump our data set or we want to dump our data, it should be in a particular format, and we have to tell Spark that in which format that it should be. So we are defining a schema here. So let me take you through the code. So I'm storing schema in a variable called schema. And we have to define the schema in a proper structure. So we're going to start with struct type. And since you know that our data set has got different fields as columns, so we're going to define this as an array of fields. So this is an array and struct. So we're defining the different fields now. So we'll start with the first field by defining it as struct field. Inside the braces, we should mention what should be the name of that particular field. So I've named it as state. It should be of string type, and true, that means it is of string type. Then next we have got fips, which is again of string type. Now I know that fips is a number, but since we are not going to do any kind of numeric operations on fips, so we're going to let it stay as string. Then we have got party as string type, candidate as string type, then votes as integer type, because we're going to count the number of votes, and there is going to be certain numeric operations that we're going to perform that will help us to analyze our data. Then we've got fraction votes, which you know is a decimal type, so we have kept it as double type. The next thing you need to do is that Spark needs to read the data set from the HDFS. So for that, you have to use this command Spark read option header true. Header true, it means that you have mentioned and you have told Spark that my dataset already contains column headers, because state and state ABBR, they are nothing but they're column headers, so it will not. So you don't have to explicitly define column headers for it, or neither will Spark choose any random row as a column header. So it will choose only the column headers that your dataset has. Then you have to mention the schema that you have defined. So I have defined it in my variable schema. So that's why I've mentioned this. So that is why I've mentioned it, and my file should be in CSV format. And then I have to mention the path of the file in my HDFS, and this is the path. And I've stored this entire data set in my variable df. Now what I'm going to do is that I'm going to divide up certain rows from my data set, because you know that my data set contains both the Republican and the Democrat data. And I just want the Democrat data, right? Because we're going to analyze the Hillary Clinton and Bernie Sanders part. So this is how you divide your data set, okay? So first thing that we have done is that we have created one more variable called dfr, and we have applied a filter where party is equal to Republican. And then we're storing the Democrat Party data into DFD. So we're going to use DFD from now onwards, and DFR, the Republican data, this is going to be your assignment for the next class. So I'm going to analyze the Democrat data, and then after this class is over, I want you guys to take the Republican data. This data set is already available in your LMS. You have got the VMs also with everything installed. So please, when you're at home, when you have free time, just analyze the Republican data and tell me what were the reasons that Donald Trump won. So I want you all to do that analysis and come up with that in the next class, and we'll all discuss about it, that whatever results and conclusions that you have made after analyzing the Republican data. And that way you'll also learn even more. And it'll be also a practice for you after today's class. So all right, so we're going to take DFD now, and the first thing that we'll do is that we'll create a table view, and I'm going to name that table view as election. So let me just show you what it looks like and what it has. So this is the command that I have run in Zeppelin. So this is the SQL code that I've run in Zeppelin, and you can see that I've got state ABBR, and I've only got the Democrat data. All right, so let's go back. All right. So after creating the table view, now every of the Democrat data is in my election table. So now what I'm doing is that I'm creating a temporary variable, and I'm running a Spark SQL code. So what I'm actually doing by writing this code, the motive of writing the SQL code or the SQL query is that I want to refine my data even more. So what I'm trying to analyze here is that how a particular candidate actually won. So I don't have to do anything with the losing data, because you know that each of the FIPS contained one of the losing candidate member and one of the winning candidate member. It contains the data of the winning candidate and the losing candidate also, because my data set contains both the data of Bernie Sanders and Hillary Clinton. In some parts, Bernie Sanders won. In some counties, Hillary Clinton won. So I just want to find out that who are the winners in a particular county. Okay, so I'm going to refine that data, and for that I'm using this query. So I'm going to select all from election, and then I'm going to perform an inner join with this query. So this is one more query inside this entire query. So let me tell you what am I actually doing. So first, what we have done is that we have selected FIPS as B. So you know that now we have got 2 entries for each FIPS. So each FIPS actually appeared twice in my data set. So I have named it as B now. And then we're counting the maximum fraction votes. So you know that in each FIP, we have the maximum fraction vote, and then we can find the winner by actually seeing who has got the maximum fraction votes. And then we have named it as A. The maximum fraction votes column is named as A, and we're grouping by FIPS. So now each of my FIPS will be selected with which has a maximum fraction vote. And I have two columns for that FIPS, which is 1001 and 1001. So only that row will be selected which has the maximum fraction votes. So now I'll have the winner data, and I've named this entire table inside this query as group TT. And then I'm validating it as where election.fips, the main table view .fips, should be equal to the B column that we have created in group TT table, and election.fraction votes should be equal to group TTA. So any doubts on this query about how I have written this? All right, so now what we're doing is that whatever data that we got here, I'm storing that in election 1. So let me just show you what is in election 1 now. So this is my election table only, and you can see that I've got two FIPS, so 1067, 1067. So now let me show you election 1. So there you have. Now you can see that I don't have repetition of FIPS. I only have one entry for FIPS, and that is the row which tells me who won in that county, or in that particular FIP, or in the FIP associated with a particular county. So you can see for Bullock, it was Hillary Clinton. For Calahoo, it was Hillary Clinton. Cherokee, also Hillary Clinton. And then State House District 19 is Bernie Sanders. So in Alaska, it's mostly Bernie Sanders. So this is what we have done now. And then you can see that we have also got additional columns as B and A. So A tells you the maximum fraction votes, and B tells you the FIPS. So the data in FIPS and the data in B are same, and data in fraction votes and data in A is same, right? So what I'm going to do now is, since my columns are repeating and they have the same value, so I don't want A and B now, right? So what I'm going to do is I'm going to filter out the columns that I don't need, and in this case I don't want B and A. So what I'm going to do is I'm going to make a temporary variable again. So I'm using the temporary variable to store some data temporarily. So I'm running the Spark SQL code to select only the columns that I want. So I want the state ABBR, country, FIPS, party, candidates, votes, fraction votes from election 1. And I'm storing everything in D winner. I've created this new variable, and whatever there was in temp, I'm assigning it to D winner. So now I have got only the winner data. So I've got all the counties, and I have got who won in that particular county, and by how much fraction votes. So what I'm just doing till now is that I'm just refining our data set so that it will be easy for us to make some conclusions or to gain some insights from that data, right? And also let me tell you that it's not always necessary that you refine your data set in the exact way that I am doing. If you have something in mind after you have seen your data and understood your data, and you found out that what actually you need to do, you can carry out different steps to do that also. This is just one way of doing that, and this is my way of doing that, so I'm just telling it to you. And then we're creating a table view for D winner, and we're going to name it as Democrat. So let me go again, and let me show you what the Democrat table view looks like. So you can press Shift Enter. So there you have, we don't have A and B column that we had in election 1. So I've just got the winner data. So now let us go back. And now what we're going to find is that I want to find out that which of the candidates won the by state. And then whatever date and whatever result I'll get, it will be stored in the temporary variable, and then I'm assigning everything that will be stored in the temporary variable to a new variable called dstate. And then I'm going to create, and then similarly I'm going to create a table view for dstate, which is state. So let me show you what my state table view actually contains. So there it is. So I've got state, Connecticut, Hillary Clinton won 55 counties, Florida, Hillary Clinton won 58 counties. So this is what we have come up to for our first data set. So now let us see what we can do with our second data set that contains all the different demographic features. So first thing, again, you have to define a schema, and this time I'm naming that schema as schema 1. And since you know that we have got almost 54 columns, so I have to mention and I have to define all those 54 columns also.
So you remember what those each columns contain. So this is exactly what I've done. And I don't need to go through every line, but I already told you how to define a schema. You can have this code in your LMS, so you can take a look at it. So the next thing we're doing, again, we have to read our data set, and then now I'm storing my data set into a new variable called df1. And this is the path in my HDFS where my data set was. And then I have created a table view for my data set, which is called fact. Now let me show you what facts contain. So you can see that it contains abbreviation, state abbreviation, population 2014. So instead of using the code now, or the encoded form that was actually there in my dataset, I have given a very meta name that will describe what it contains, right? So instead of PST 214, I've got population 2014. So that makes sense, right? It contains all the 54 demographic features or different features that was in my dataset. White alone, not Hispanic or Latino, living in the same house 1 year and over, foreign-born persons, language other than English, spoken at home, high school graduate or higher. So it contains basically all the different features or all the different columns that actually was in my dataset and that I have defined it in my schema. So this is what facts have. So now what I'm going to do is that I'm not going to analyze my whole data based on all these different features. I'm just going to choose some specific features in order to analyze it. I'm going to just take a few at one. So these are the different features that I'm going to use. I'm going to use FIPS. I'm going to use states. I'm going to use state ABBRs, then area name, candidate, and people who are over 65 years, the senior citizens, and then female people, white alone, black or African alone. I'm choosing Asian alone, Hispanic or Latino. So basically what I'm trying to do is that I'm trying to check what is the popularity of Hillary Clinton among the foreign people or people from different ethnicities. So I'm choosing white people, black people, and Hispanic people. So I'm just trying to analyze it, okay? And you know that I've stored this in a temporary variable again, and then whatever result I'll get by running the Spark SQL code, I'll store it in a different variable called dffacts. And then I'll store it, and then I'll make a table view for dffacts as winner facts. So let me show you what winner facts look like. So it's winner and underscore facts. So we have got the FIPS, the state is Alabama, the state abbreviation is AL for Alabama, the area name is Ottawa County, the winner was Hillary Clinton, and the people over 65 years in that particular county is 13.8%, female percentage is 51.4, white alone is 77.9, and so these show you the data. So black or African is 18%. And then I've got the different fields that I've selected, Asian alone, Hispanic or Latino, foreign born. So I've chosen 14 features to analyze it from. All right, so now what I'm doing again is that I'm going to divide the Hillary Clinton data and the Bernie Sanders data so that we can analyze only why Hillary Clinton won or why Bernie Sanders won in some particular counties. So we are applying the filter the same way we divided Democrats and the Republic data from our initial primary results data set. So this is what we have done. So you know that's stored in dffacts. So we're putting a filter in dffacts and where candidate is equal to Hillary Clinton. So that will be stored in 8C. And then the data of Bernie Sanders will be stored in BS. So after that, what we're doing is that we're doing a one-hot encoding. So we'll add two more columns in our data set as W underscore BS and W underscore HC. So in this case, we're going to do one hot encoding, and what we're going to do is that, so we're going to include or we're going to attach two more columns in winner facts as WHC and WBS, and it'll just contain either 1 or 0. So it is in the way that in whichever county, so if you're considering a county, let's say Ottawa County, so if Hillary Clinton is the winner, it will have 1 in WHC, and in WBS it will have 0. Similarly, in whichever counties Bernie Sanders won, so Bernie Sanders will have 1 and then WHC, so WBS will have 1 and WHC will have 0. And then we're creating different views for both of these two together. So this will only tell me wherever W8C is 1, that means so it'll only show me the counties where Hillary Clinton won, and this will only show me the counties where Bernie Sanders won. Okay, and we're creating a view for both of these. So for Bernie Sanders, the view is WBS, and for Hillary Clinton, it's W8C. And then finally, we're merging both of them together using union. So select all from W8C, union all, select all from WBS, and finally, we have stored it in result, and we have created a table view known as result. So let me show you what this result contains. So there it is for Ottawa County. It was Hillary Clinton. So we've got the Bernie Sanders data over here at the bottom. So there. And I've got all the different fields also from my second data set, the different features that I chose from my second data set to analyze it. So now comes the actual analyzing part. This is where we're going to perform k-means. But first we have to define the feature columns. Actually, you have to define what is the input that you're going to feed so that you get an output. So this is actually the input that you're going to feed to the machine so that some machine learning goes on and finally it gives you some kind of result, right? So this is where I'm defining. So again, I'm using an array to define all the different fields from my data set. So I'm using person 65 years and over, female person percentage, white alone, black or African American alone, Asian alone, Hispanic or Latino, foreign born persons, language other than English, spoken at home, bachelor degree or higher, veterans, home ownership rate, median household income, persons below poverty level, and population per square mile, and W8C and WBS. And then I'm going to use the vector assembler. So this will enable me some machine learning. So this is what enables different machine learning algorithms where we're using k-means. So my input column is feature call. So this is going to be the input, and my output column will be called as features. So whatever result that I'm going to get is features, and we have to transform results. So this is the final table view that we have created, and you know what transforming means. Transforming again means, so in our strategy, we already saw that we have to transform the data first. So my updated data set was result. So I'm going to transform result. Input columns is going to be these, which is feature calls, and my output table view will be called features. And then we're going to perform the k-means clustering. And we're going to store it in a variable called k-means. So we are using different functions. So we're going to use different functions from Spark MLlib library, and we have chosen Spark ML clustering k-means. And you know that in k-means, we already defined that how many clusters do we need, and we need 4. So we have selected 4 clusters, and then we are going to set feature columns as features, and then set prediction column as predictions. So after that, we're going to make a model. So we have defined our input-output columns in rows. So we're going to use k-mean fit row. So whatever predictions that we'll get, we're going to store it in model. And then what we're going to do is that we're going to print the cluster centers for each cluster. So let me show you what my cluster centers are. So after we have run this code, so you can see that these are the different cluster centers. Just so that I can make you understand about what we're going to do after k-means clustering, how to analyze it. So the numbers are present, they're placed very haphazardly. So what I've done is that I have picked out each of the cluster center points, and then I have made a new table. Yes, so this is it. So you know that we have got 4 clusters. We have got the 0th cluster, first cluster, second cluster, and third cluster. So 0, 1, 2, 3. Okay, so 4 clusters. And we have found out this cluster centers according to different features that we fed into my k-means algorithm. So what we observed here in W8C and WBS is that the winning percentage, or the winning chances of Hillary Clinton, was 0.9, whereas winning chances for Bernie Sanders was 0.1. And then if you observe the differences in the cluster centers for each feature, here you can see that there is not much difference. Not even here, so it's 50, 49, 49, 51. And then in white alone, again, it is not much of a difference. But if you see here that it's 9 and it's going to 16. So you can do a more detailed analysis on Black or African American. So if you want to know the real support of Black or African American, you want to see what was their voting pattern, how popular was Hillary Clinton among them. So maybe this would be a good field to analyze because you see the variations in number. Similarly, you can check out other features too. You can check out here at 16, 8, 9, and 36. So maybe again, Hispanic or Latino field, you should make some more analysis on it. And even here you can see in veterans there is 47,806, whereas we have got 182,000 also. So there is also a lot of difference. Here is only 2,759. We've got in 10,000s, we've got numbers in even 100,000s here. So this is how we can identify that which are the fields, or we can find out the main reasons or the main points where we should make our analysis on. So let us go back to our Zeppelin notebook. So here it is. So now what we're doing is that we're going to visualize the result first. So we're counting from prediction. So you can see that in cluster 1, so the prediction means prediction contains my cluster. Since you know that I have stored my clusters, my cluster information in prediction, this is my output after the k-means. So I have got these many clusters. So this is the count of my counties or count of different areas that lie in my particular cluster. So you can see that in cluster 1, I've got 1,917. In cluster 2, I've got 751. So maybe I should pay more attention on analyzing cluster 1, right? So that's why I have selected cluster 1 here, and we're making different predictions. So you can see that in x-axis, I have got foreign-born people. And in y-axis, I have chosen language other than English spoken at home. And then we're grouping it by candidate. So you can see the lighter blue is for Bernie Sanders and the more dark blue is for Hillary Clinton. So all this light blue is for Bernie Sanders, and you can see that as the number of foreign people increases, you can only see Hillary Clinton in the scatter plot here. So there might be a few outliers like here, and the size is defined according to Black or African American alone. So you remember that this was the feature where we find a lot of variations in the numbers. So that's why we grouped it according to that. And you can see the bigger the circle, it represents more Black or African American alone. So what is the conclusion that we can find out from this scatter plot? We can see that as the number of foreign people increases, the popularity of Hillary Clinton is more in larger groups of foreign people. You can also choose different parameters out of all the different features that you have chosen. So remember that we have also seen the variation in veterans. So let us choose veterans in y-axis. So let us also change x-axis. Let me just choose white alone here. So what you can see here is that this is the x-axis that has white alone, and this is the veterans. So you can see that Hillary Clinton is popular among veterans also in a smaller group of veterans, since we have decided the size on Black or African American alone. So the size also represents some value. So she is popular among the African American veterans. And then as you go ahead, and as the count increases, you can see actually there, since it's a scatter plot, and it almost represents that this is a point as the number of people increases or as the number of white people increases, the votes are equally kind of distributed between Bernie Sanders and Hillary Clinton, because there are a lot of points in this scatter plot over here. So you can go ahead and drag and drop different features, and you can make different visualizations on that. So now what we have done is that we know that there are 1,917 counties in my cluster 1. So what I'm going to do is that I'm going to see that among this 1,917, how many were in favor for Hillary Clinton and how many were in favor for Bernie Sanders. So in cluster 1, you can see clearly Hillary Clinton is the winner, and Bernie Sanders only has got 764, whereas she has got 1,153. Similarly, in cluster 3, again, Hillary Clinton is the winner with 9 and Bernie Sanders with 1. Then in 2 also, she has got 388 and Bernie Sanders was 363. So this was a very close call. And again, in 0, you have got 119 and 30. And then we went ahead and created a line chart also of the vote distribution for Hillary Clinton and Bernie Sanders. So In keys, we have selected prediction, and the values here are WHC and WBS, the sum that we have got over here. So definitely Bernie Sanders is lagging behind. So even though you didn't have that table for you, you can also find it out according to this line chart. So you can see that in cluster 0, so you can see here that in cluster 0, even again, Hillary Clinton was ahead of Bernie Sanders. So in cluster 2, there was a very neck-to-neck competition, and you can see it in the graph here. So this represents cluster 2. So you can see they have a neck-to-neck competition, and again in cluster 3, they have got a neck-to-neck competition. So this describes the distribution of votes for Hillary Clinton and Bernie Sanders, and definitely Hillary Clinton was ahead, and that is why, of course, she won the primary elections. So again, you can go ahead and make the same. We have created the same graph. It's only just an area graph instead of a line graph. So the keys here are state and candidate. So I've got states and candidates over here, and then the values is counties one. So if you just hover on to this bar chart, so you can see that in Connecticut, Bernie Sanders won 115 counties. In Connecticut, Hillary Clinton won 55 only. So in Florida, Hillary Clinton is 58, and in Florida, Bernie Sanders is 9. So here you can see in Maine, Bernie Sanders won 462. So Bernie Sanders got majority votes from Maine. So you can also classify it state-wise. You can also find out that which are the states. So as Donald Trump, now you'll know that which are the states that you can target, right? So you know that in Maine, a lot of people vote for Bernie Sanders. So maybe Hillary Clinton is not popular. So you can go ahead and lead out. So as Donald Trump's party member, you can just advise him to go in Maine and carry out different campaigns, because Hillary Clinton is not so popular there. So maybe it would be a little easier to get the votes from the people of Maine. So this is what you can make conclusions. So this might not be very accurate, but this will be very close. So the thing is that you can make different charts. You can make bar charts, you can make pie charts. So whatever county is one that we have made in a bar chart, so this is there in a pie chart. So this looks better, but maybe it's not insightful. I just placed it so that I can show you that you can make pie charts also. So these are the insights that you can make after analyzing your US county data. So this is what you can tell Donald Trump. So these are the different suggestions that you can actually go and tell Donald Trump that she is popular among the foreign-born people and the people who speak different languages. She is popular among the Hispanic people. And then in Maine, she lost in a lot of counties. She almost lost in all of the counties in Maine. So these are the different insights that you have got, and then you can tell your superior or your employer who has hired you to do that. So this is what you can present, right? So this is for a very beginner's level way. So there is some more analytics that you need to do. I just showed you a few options. You can go ahead and try more in the Democrat section also, and you remember that you have to do it for the Republican part also. So let me see that what you have learned today. So, but if you have any questions right now, you can just go ahead and ask me. So does anybody have any questions? All right, so Ajay is telling that I will give it a try and ask you in the next class. Of course, Ajay, you can. I'm very happy that you found it interesting and you are going to try. So, all right. Thank you, Ajay. So now we'll move on to find out the solution for the instant cab use case. So remember that we have got the Uber dataset, which contains the pickup time and the location by 2 columns, latitude and longitude, and then we have also got the license number for a particular Uber driver. And what we have to do is that we have to find the beehive locations. That is the point where we'll find the maximum pickups, and then we also have to find out what is the peak hour of the day. So this was the entire strategy. So we have got the Uber pickup dataset, and then we will store the data into HDFS. We'll transform the dataset and make predictions by using k-means clustering on the latitude and longitude to find out the beehive points. So now let me open my other notebook, the Uber notebook. So again, the first thing that you have to do is copy the Uber dataset into your HDFS. So I've already done that before explaining you the US county analysis. So again, the code is kind of the same. The first thing is that, again, we're importing some Spark SQL packages and some Spark MLlib packages, because we're again going to use k-means clustering. So you can see the vector assembler here again, Spark ML clustering, k-means. and other Spark SQL packages. So then we have to start our SQL context, and we're doing it the same way. Then the first thing, again, we have to define a schema. So now I don't have much fields. I've got only 4 fields, if you remember. So the first field was the date and timestamp that defines the time. So we're defining it as dt. And the next field is the latitude, the longitude, and the base. And then I'm going to read my data set, and this is the path in my HDFS where my Uber data set is there. So I have defined the schema here. The header is true because, of course, again, my data set contains column headers, and I'm going to store it in df. So my feature calls here is going to be latitude and longitude because I'm going to find out the beehive point, the point where I'll get the maximum pickups from. So again, I have set the input calls as feature calls here and output calls as features. So I'm using the assembler to transform my data set. And then again, I'm using k-means, and we use the same elbow method, and we found out that we should make 8 clusters for this data set. Okay, and then we're selecting the prediction column or the output column as predictions. And then again, we have printed the cluster centers for each cluster. So definitely whatever result we're going to find, the cluster centers will tell me the exact location. So this cluster centers that we'll find after k-means is actually the beehive point. So this will be the point where I'll find the maximum pickups, right? So here I have printed my cluster center. So this defines the latitude and longitude. So this is going to be my location where I'm going to find the maximum pickups. And I've got 8 results like that because I've got 8 clusters, and it defined the centers for 8 different clusters. So this is exactly like the school problem that I explained to you in k-means. So this is what exactly happens. So since we found out the center of each cluster, and that is where we're placing the school or building the new school. So similarly, this is going to be my beehive point. This is where I'll place maximum of my cabs. Okay, so we found the beehive point. So the next thing that we need to do is we need to find the peak hours, because I also need to know that at which time should I place my cabs into those locations. So what we're doing now, that we're taking a new variable called q, and we're selecting hour from the timestamp column, and then the alias name should be hour, and we're getting it from our prediction or from the result that we got after my k-means clustering. So now we're grouping it. It will have the different hours of the day, and then it will just show me the pickups at the different hours of the day in the location that we found out are the beehive points. And then we're going to count that how many pickups are we going to get from that place, right? So, and we're ordering it by descending. So the smaller pickup count will be on first, and then the larger would be at the bottom. Similarly, again, we're creating a new variable called t, and we're doing the same thing. So here what we're doing is that we're selecting the time, the hour of the day, the latitude, longitude, prediction, and then we're filtering it by hour, which is not null. So we're filtering out the null values from here. So now we have created a table view for categories. So let me show you what categories contain. Okay, let me just go down. So I've done some few operations here. So I'll scroll back up and I'll show you. And again, we have created table views for T and Q also, which is again T and Q. All right, so, and then I've made some visualizations for each. So then we have created a value P where hour is not null. So again, we have filtered out the null hours, and we have created a new view called P. So here is my hours. So this is my count in the x-axis, that how many pickups were there, and this contains different hours of the day. And then I've grouped it by prediction. The size is according to the count. So you can see that the bigger the circle, it means more the pickup. So you can find out the biggest circle, and you know that you can find the biggest circle as you go along the x-axis, because this is where the count increases. So you can find out the biggest circle would be here, and it lies in my 4th cluster. You can see that there are 8,915 pickups at the 17th hour of the day, which is around 5 p.m. And so you know that the maximum pickups are around 4 o'clock or 5 o'clock, and it lies all in my 4th cluster. So it means that my peak hours are around 4 or 5 o'clock in the evening. Right, so this is what insight that we have gained. So you can tell your instant cab CEO that I found out that, so your cab should be ready around 4 or 5, because maybe that's the time when people go home from offices or they are going out for dinner or something. And this is what my another table view looks like, which is T. So here we have latitude and longitude. So this is where we are finding the beehive locations. So I've got the distribution in a scatter plot again, so you can see that we have got very dense points over here. It means that these represent the beehive points. So what you can do is that you can just put a US map and scale it according to this scale over here, and then you can exactly find out that what is the exact location where you need to put your caps around the 17th hour or the 16th hour of the day. All right, so, and you know that we had a lot of rows, but the results are only limited by 10,000. You could just run 10,000 rows, but we obviously had a lot more. And then you can check in different clusters. So we have selected from the cluster. So now we're analyzing cluster 0. So here, if you see this point over here, this lies in cluster 4, this lies in cluster 5, and this lies in cluster 0. So you can just analyze each cluster also. So here I have just laid out the latitude and longitude for my 0th cluster. So you can see here where prediction is equal to 0, and I'm selected this from the table view of T. So there you can find out the exact latitude and longitude for, so here the latitude is 40.722 and longitude is negative 73.995. So this is how you can pinpoint location where your cabs should be during the peak hours. So again, if you see this distribution, this is a pie chart that I have created, which just tells you that what is the count of pickups at each hour of the day. So there are 20, so starting from 0 to 23, there are 24 slices in this circle. So you can see that these few slices are the bigger chunks. So this is the 19th hour of the day, which is around 7 o'clock, 6 o'clock, 5 o'clock, 4 o'clock, 3 o'clock. So, and you can see in the midnight, maybe nobody travels more. So maybe your cabs can rest, or you don't have to place more cabs during this part of the day. So these are the insights that you can gain. So any questions on that? So I think after doing the US county election, this was pretty easy to do. And this was also pretty easy to understand. And the results were also much, much clearer, right? Okay, so let us go back to our presentation. So now let me tell you about the Edureka LMS that you have. So you will have everything in your LMS. All these classes are recorded and they will be there in your LMS. So even if during this class, if you forgot something that I said, so you can just take a look at this recording of the class again in your LMS. So you can just go ahead and learn on your own. So you have all your course content, your self-paced course. So whatever documents that you want related to your subject, so you all find it here. So let me just show you that. So even the entire course content is here. So whatever documents, whatever presentations, and all the recordings will be here in the course content according to different modules. So you also have access to different projects related to your course. So you can just download all the problem statement, all the requirements that you need to do in order to do this project. You can just download it, and after solving it, you can just submit it here. And again, you have the Edureka VM. So there is also proper guideline mentioned about how to use this VM. And if you have any doubts, you can call our 24/7 support team also. So let me just show you the LMS. So you just have to go to edureka.co. So I'm already signed in. So if you're not signed in, so there will be a sign in option here at the right corner. So you can just sign in and then just go to courses, go to my courses. So here are my different courses that I have bought from Edureka. So you can just go to course. So here is everything that you want to get started with Hadoop. So you have got everything mentioned here, the software and hardware requirements. So you can click here to access Edureka VM installation guide. Then this is the entire guide for your LMS also. Then you've got all the pre-recorded sessions over here, class 1, class 2. So you can watch anytime you want. And the best part of your LMS is that you'll have a lifetime access to it. It is not like that once your classes are over, once you have learned Hadoop and your bachelor's is over and you're not attending any more classes, you can still have access to all the older classes that you attended, and you can view it any time you want. Then there is the course content, there is for module 2, there is the class recording, there is the module presentation, the quiz, assignment, and everything. And again, I'm telling you, if you have any doubts about how to use the LMS or how to use the virtual machine, you can always call our support team. So does anybody have any questions? All right. Thank you for attending this session. I hope you had a good time in learning about Hadoop and Spark. You can rate us to let us know that how much you have enjoyed learning with Edureka. You can comment your experiences. You can even give us some suggestions. Don't forget to like this video if it really helped you. You can also help us to get some more ideas about what we should come up with next. And then you can also take part in our survey so that we can improve us more. So thank you for watching this video, and I'll see you next time. Till then, happy learning.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!